How are you all doing this morning?
Doing all right.
All right, I got a little bogged down with some technical difficulties yesterday. I didn't even know my Surface Pen ran on batteries, and apparently it did. It died, and I had to go to 4 stores to find batteries. So I kind of ran out of time to make a video for today. So we're going to have a live-ish lecture on filters.
All right.
One thing that I've received a couple of emails about, and I guess I need to address, which let me look something up real quick, is getting your grades and all that kind of stuff back to you before the drop date. So I have a test to make for circuits 1 today and probably tomorrow, and then after that I'm going to spend the rest of the week grading your exams and as many homeworks and all that kind of good stuff as I can get through, so that you'll have hopefully a good idea where you stand in the class. But I don't think anybody's in any real risk of danger. That being said, I've graded nothing, so I might be wildly wrong. I'm going to spend the rest of the week trying to catch up on all the grading and stuff that I have not done in this class to this point. Alrighty, so let's share this here screen. Let's start talking. All right. So, do you guys have any idea what it is that a filter circuit does? Let's start there.
I can take a guess.
Take a stab at it.
Does it filter out noise and like a sinusoid or something like that?
That could be one application of the filter. Absolutely. Say you have something to add?
It can really filter out like whatever frequencies you want. Like you can have high pass or low pass filters.
Yeah, exactly right. It's a so Devin, when you said noise, that's not wrong, but it depends on what the frequency spectrum of the noise is as to whether or not it will be filtered or not filtered in an electrical filter. So if you think about like your car's oil filter, okay, you have a filter. I'm just going to draw it as a black box. And then you have 2 inputs. One input is oil. I can get this stupid box thingy out of the way so I can draw there. Let's see. And the other input is dirt, really, right? There's a mixture of oil and dirt that goes into the filter. And then the output is, hopefully, if your filter is doing its job right, only the oil that gets recirculated back through the system. And an electrical filter does a much similar thing, but it screens on the basis of frequency. So electrical filters rely on the fact that the impedance of a capacitor and the impedance of an inductor are frequency dependent. So hopefully you guys recall at this point that the impedance of a capacitor is 1 over j omega c, and the impedance of an inductor is j omega l. Well, if we look at these impedances as a function of frequency, we could see that when the frequency is low for a capacitor, we're going to have 1 over 0, which is infinitely large, and it's going to trail off to 0 as frequency increases. And when we look at an inductor, we have the opposite, right? When the frequency omega is 0, the impedance is 0, and as the frequency increases, the impedance increases. And we can use those simple relationships to build filters capable of passing only certain portions of the frequency spectrum while rejecting others. So we're going to first talk about some ideal filters. And Sadie kind of already set us up for this because she mentioned a few of them. So an ideal filter, there are 4 different types. And I guess I'll just draw the responses actually here. So the first one that we have, or that we'll be considering, where this is the magnitude, this is frequency. So let's see. So we're going to call its maximum magnitude M naught, and we're going to call the frequency where it switches from passing to not passing omega C, which is what's called the corner frequency, or commonly the cutoff frequency. And so this particular filter has a pass band, which means that every frequency below omega C gets passed, and then every frequency above omega C gets stopped. So this would be an example of a low pass filter. And it's an ideal low pass filter because it has this, what we call a brick wall frequency response. So there's a very abrupt shift between the pass band and the stop band, so that omega C definitively constricts which frequencies get passed and stopped. We can also have the opposite. So this on the right-hand side, so for higher frequencies, we have a pass band. And for lower frequencies, we have a stop band. And this is called a high pass filter. It has the exact opposite behavior of a low pass filter. So everything above omega C gets passed and everything below omega C gets rejected or stopped. And these can be realized with effectively any order of filters. So first order filters and beyond can perform high pass and low pass operations. And that's mainly what we're going to be concerning ourselves with today. But there's also 2 more filters that we'll be talking about. Let's see, let's call this omega naught, omega C1, omega C2. And in some textbooks, you might see those omega C1 as omega low and omega C2 as omega high, where this middle region is our pass band. And then we have 2 stop bands, one on each side of the pass band. So this is what's called a band pass filter because it passes all frequencies within a specified frequency band from omega C to omega 2. And then lastly, we have the opposite of a band pass filter, which is what's called a band stop filter. where this is our stop band here in the middle. And then we have two discrete pass bands. And the band stop filter may also be called a notch filter because there's a notch cut out of the frequency response where that selects the frequencies. And band pass filters and band stop filters require at least a second order circuit. So let's talk about what I mean by first order and second order circuits with respect to filters. And the short answer is that it means the exact same thing as it does when we were talking with respect to transient analysis problems. So a first order filter contains one energy storage element. So it's going to have a resistor or some combination of resistors, and then either a single capacitor or a single inductor. And our second order filters will be RLC circuits, or they'll have two discrete capacitors or two discrete inductors. So second order circuits have two energy storage elements. First order circuits have one energy storage element. All of these filters are defined by a couple of parameters here, particularly the amplitude and the cutoff frequency. And we're going to observe that practical filters, so non-ideal filters, can still be characterized by those two things, but the response is going to be pretty different. And the reason is because, let's see, how do I explain this? Instead of having these abrupt, almost stair-step-like responses, or these brick wall responses as I've described them previously, they're going to be a lot smoother. So there's going to be a smooth transition between the pass band and the stop band of all of the practical filters, as opposed to the abrupt transitions that we're seeing in the ideal filters. And this is because those energy storage elements that are used can't give up all of their energy instantaneously. So let's jump to a new page. The response of a practical filter is mathematically described by what's called the transfer function of the filter system. So if we have a generic filter, like so, where the left-hand side is the input side. And so I'm going to call this VN phasor. All of these are going to be frequency domain quantities. This is IN phasor. This is our linear filter circuit. Here's our output side. We could have an output voltage or an output current. And what our linear filter circuit does is it acts on the input to produce the output, where the understanding is that the output is simply a portion of the input. So there are four different transfer functions that we could be paying attention to. We have the voltage transfer function, which is the one that we're going to be dealing with. So I'm just going to call it H of omega. And that is defined as simply the ratio of the output voltage as a function of frequency divided by the input voltage as a function of frequency. So it's the exact same thing as the voltage gain that we use for our op-amp circuits and stuff like that, except that now things are allowed to vary with frequency. Then we have, we could have a current transfer function. So that would be I out divided by IN, both as functions of frequency. We could have a transconductance transfer function. Would be I out divided by VN. And we could have a transresistance transfer function, which would be V out divided by IN. And in later classes, where we go? Yeah. In later classes, you might actually deal with some of the other transfer functions, but for circuits 2, we are going to restrict our analysis to this simple voltage transfer function. It's going to give us the information that we are looking for. So let's consider then a fairly simple circuit to analyze and determine the transfer function. So let's say that I have a simple RC circuit in the frequency domain. So I'm going to characterize the capacitance by its impedance, 1 over j omega c. And on the left-hand side is my input voltage, Vin. And on the right-hand side is my output voltage, Vout. Our goal here is to find a relationship between the input voltage and the output voltage. So do either of you have any ideas how we might approach that?
I mean, is it just going to be like a nodal or something?
So nodal might be overkill here, right? So let's say, for argument's sake, that we know what our input voltage is. So it's well defined. What I would suggest that we do here is that we call it 1 angle 0 degrees, where the frequency doesn't matter. That's one thing that's kind of important here. We're working with phasors, but the excitation frequency is allowed to change. So if we had 1 angle 0 there at the input, how can we calculate V out?
Should just be whatever that capacitor is, right?
Yeah, it's just the voltage drop over the capacitor. Absolutely. So from the perspective of the input voltage, we see a resistor and a capacitor in series, and we just want to know what the voltage drop over the capacitor is. That's how we'll analyze the circuit. And so I would suggest that we employ voltage division. So using voltage division, we can see that V out is going to be V in, which we can consider it to be 1 angle 0 or whatever you guys want, multiplied by R plus 1 over j omega c in the numerator, or excuse me, in the denominator, and just 1 over j omega c in the numerator. And I'm going to go ahead and clear some of these fractions because I don't like this particular fractional form. So I'm going to multiply by j omega c over j omega c, and that's going to leave me with Vn as a function of omega multiplied by 1 over 1 plus j omega rc. So has the algebra that I've done there make sense? Multiplying both sides by j omega c, or the numerator and denominator by a factor of j omega c, I guess is the way to express that.
Yeah, it looks fine.
All right, so our transfer function then which, if you recall from a couple of minutes ago, is simply V out divided by Vn is then 1 divided by 1 plus j omega rc. So our transfer function for these circuits is going to be a complex number. And a complex number can be broken into two distinct parts, its magnitude and its phase angle. And we'll see that for these filter circuits, the magnitude is going to vary with frequency and the phase angle is going to vary with frequency, and that's important. The phase angle varying with frequency is another deviation from the ideal op-amp brick wall responses we had there. There was no mention of any phase angle because it was assumed that it stayed constant, but we're going to see that the phase angle is going, we're going to experience a phase shift with increasing frequency in these circuits. So what I'm going to do now is I'm going to expand this guy a little bit more. I'm going to multiply this by the reciprocal of the denominator in both the numerator and the denominator. So I'm going to have excuse me, not the reciprocal, the conjugate, 1 minus j omega rc divided by 1 minus j omega rc. And what this is going to do is it's going to make my denominator purely real and make my numerator a rectangular imaginary number so that I can split things up. So let's work on the denominator first. I'm going to have 1 times 1, so that is 1. And then I'm going to have plus j omega rc times minus j omega rc. So that's going to be negative j squared, which is positive 1, omega rc quantity squared. And in my numerator, I'm going to have a 1 for the real part, sorry, minus j So this is me breaking up my transfer function into a purely rectangular complex number. Anybody have any questions, comments, or concerns about the complex math I just did there? All righty, so from this, let me go down one more. Come on, stupid. There we go. Our magnitude, which is going to be h omega, but no bar over it because it's no longer going to be a complex number, is the real part of h of omega squared plus the imaginary part of h of omega squared. So I get the magnitude of a complex number And so this is going to look like so I'm going to have 1 squared plus omega RC squared, omega RC quantity squared, divided by 1 plus omega RC quantity squared squared, which leaves me with this. So this is what my magnitude, excuse me, mathematically will look like. And in a moment, we'll pop over to maybe LTSpice and Mathcad actually to look at things. For our phase angle, theta as a function of omega. From our complex number relationships, we know that it should be the arctangent of, actually, it's not on the brace, the imaginary part of h of omega divided by the real part of h of omega, which is going to give us inverse tangent of, see, the imaginary part is negative omega RC divided by the real part is 1. And so that's going to give us negative inverse tangent of omega RC. There we go. So that is the magnitude response and the phase response of this circuit. Now we can actually figure out whether or not this is a low pass filter or a high pass filter right now by doing something pretty easy. So what I want us to do is figure out what h of 0 is and h of infinity is. So only looking at the magnitude part. What's if omega was equal to 0, what would we have?
Is it just 1?
Right, so it's going to be 1 divided by the square root of 1 plus 0. So 1 over the square root of 1 is 1. What happens at infinity?
Goes to 0.
Goes to 0. All right, so our filter's response starts off high and goes to low as the frequency increases. So what kind of filter is this?
Low pass.
Exactly right. So this simple test can tell you whether it's a low pass filter, a high pass filter, a band pass filter, or a band stop filter. So for a low pass filter, it should go 1, 0. For a high pass filter, it should go 0, 1. For a band pass filter, it should go 0, 0. And for a band stop filter, it should go 1, 1. So that's just a very simple test that we can do. All right, so let's look at LTSpice real quick. Which means I have to open LTSpice. Hopefully this all works out well. It's been a hot minute since I've done this, but it should be groovy. All right, so we're not going to be dealing with a DC voltage source. We're going to be dealing with a small signal AC voltage source. So we're going to say that its AC amplitude is 1 and its phase is 0, and we're going to leave it alone. We're not going to mess with any of the other stuff on the left-hand side because we are going to want to be able to sweep this. So we're just giving it its initial parameters. Then
Are we supposed to be able to see it right now?
Oh, crap. Good call. Thank you. So let me delete what I just did. Let me move this thing out of the way. All right, so what I was saying, so I'm going to drop a voltage source in. And we're going to have to go to the advanced settings. And instead of messing with anything on the left-hand side, we're going to come over here to the right-hand side, and we're going to give it an AC amplitude of 1 volt and an AC phase of 0. And that's it. That's our only parameters. We're going to wire up next a resistor. And I'm just going to arbitrarily give this guy a value of 1 ohm. And then lastly, we're going to wire up a capacitor, which I'll sneak in there in a second. We're going to give this guy a value. My right clicking will work finally. 1 farad. And need to establish my ground, which will be this bottom node. And we're going to do let's go to simulations. We are going to do what's called an AC analysis on this. So the type of sweep, let's go decade, number of points per decade, let's call it 100. The start frequency, I want it to be at 1, well, let's say 10 millihertz, and the stop frequency should be 100 hertz. I think that'll work. And let's run the simulation. All right, so no errors. So that's good. All right, so let me make the response larger. Okay, so hopefully you all can see this here graph. So it contains 2 pieces of information. The first piece of information is the thicker green line, or the not dotted green line. Hopefully you guys can tell the difference here. But the not dotted green line is the magnitude response. And this is what's called a Bode plot. It is logarithmic on both the x-axis and the y-axis. And the y-axis is specifically measured in what's called a decibel, where a decibel is simply 20 log times the magnitude response, or 20 log of the magnitude response. The dotted green line is the phase response, and it's given to us in degrees. So we see that for the magnitude response, we start off at 0 decibels, which is effectively 1. And then after a certain amount of time, it falls off to and starts decreasing at a specific rate that's usually measured in decibels per decade. So that would mean if we started looking at, like, notice that it looks like a straight line here. So if we look at the graph at 1 kilohertz, we can see that the magnitude is negative 16 dB, and at 10 kilohertz, which is 1 decade later, it's at negative 35. So it's dropping at roughly negative 35.9. So it's decaying at roughly negative 20 decibels per decade. That's how we would quantify this slope and the response of the filter. So let's talk a little bit about the corner or cutoff frequency while we have this graph up and we can kind of look at things. So for the ideal filters, the cutoff frequency was very easy to determine, right? It was just everything below this point was passed and everything above this point wasn't passed. But because we have a smooth transition between the pass band and the stop band for a practical filter, we need another definition. So we are going to define the cutoff frequency to be when this signal drops by 3 dB. So if it starts at 0, we need to find when it hits negative 3 decibels. So I'm just dragging my mouse over. Here we go. So it's hitting a frequency of minus 3 dB from its maximum value at roughly 160 millihertz. Now that probably doesn't mean a whole heck of a lot to any of you guys, and that's perfectly reasonable. But if we pop back over to our notes here, I can give you a mathematical relationship. Can you see the notes?
No.
Okay, you're still seeing LTSpice. That's fine. I just wanted to make sure before I went off and started yammering about stuff. All right. So our cutoff frequency in our mathematical model is going to happen whenever our maximum value of the magnitude, or when our magnitude falls to the maximum value divided by the square root of 2. Cutoff frequency is where M is the frequency where cutoff frequency only piece. Sorry, no, don't erase. Occurs is the value of omega at which the magnitude M is equal to M naught over root 2. In this case, M naught, our maximum value is 1, and it's going to be 1 for all of our most basic, what I'm going to call passive filters, because they don't contain active circuit elements like op amps. So for our low pass filter that we have just described, we want 1 over square root of 1 plus omega RC quantity squared to equal to 1/2. So under what condition or under what value of omega is that going to occur? Sorry, 1 over square root of 2.
Wouldn't it also depend on the resistance and capacitor?
So yeah, it is absolutely going to be some relationship having to deal with the resistance and the capacitor that I'm trying to get you guys to tell me what it is. So if we want this fraction on the left-hand side to be equal to 1 over the square root of 2, that means that we want omega RC squared to be equal to 1, right? Because then we would have 1 over the square root of 1 plus 1, which is 1 over the square root of 2. Does that line
Oh,
up?
okay. Yeah, I interpreted the question wrong.
So my question then is, what value of omega is going to make this bit look like 1? Can anybody do this crazy, what I thought was simple algebra that I've set up right down here?
I feel like I should be able to,
What
but
happens if we divide both sides by RC?
Do we, oh, so you just wanted it in terms of RC. Okay.
yeah, that's what
Yeah.
I was confused about.
All right,
Yeah, just 1 over RC.
there we go, 1 over RC.
I thought you wanted like an actual numerical.
Well, we don't know what R and C are for our generic case that we have come up with. Okay. Now, in the example problem that what I did on LTSpice, we had R was equal to 1 ohm and C was equal to 1 farad. So let's take a look. So 1 over 1 ohm, which is a volt per amp, times 1 farad, which is a amp second per volt, so let's see, the volts cancel, the amps cancel, and we have 1 radian per second, I believe. Now, if you recall, LTSpice told us that our our cutoff frequency was approximately 160 millihertz, but that is a linear frequency, and we are looking for an angular frequency. So if we take that 0.16 hertz and multiply that by 2 pi, we get 1.005, etc. radians per second. So our simulation results match exactly what our numerical results tell us it should be. It's just they're in different units, so we need to be careful there. Is that clear? So LTSpice gives us everything in degrees and linear frequency, and we are looking at stuff with angular frequency when we do the math. So we need to pay attention and recall that 2 pi times the linear frequency is equal to omega. Okay, so let's see, what do I want to do now? Let's hop on to Mathcad. If I can find Mathcad, there we go. We can also use Mathcad to verify things, which could be useful. Once Mathcad finishes opening. There we go. Go away. So we're going to start find R is equal to 1. And for whatever reason, Mathcad, on the plot I'm about to make, well, let me just show you. So R is equal to 1 ohm, C is equal to 1 farad. I'm going to say that H of omega is equal to 1 over 1 plus J times omega times R times C, right? This was our original transfer function. I can't put a bar over H here or it will interpret it as I want the complex conjugate of this to be that. So we're going to have a slightly different look of things just because I can't bold it or anything like that either. It's just the limitations of using Mathcad. So I've defined what H of omega is. I can graph it as well. So if I go to plots and I insert a plot, I can define what I want to be plotted. So I can't plot H directly because it is a complex number. So I can plot the absolute value of H, which is by definition the magnitude and down here I should put and it's probably going to give me an error. Yeah, and it says replace your complex values and not numbers by real numbers. I don't know why it keeps telling me that, but if I delete these units up here, it fixes it. Now this plot looks decidedly different than our LTSpice plot. And there's a couple of reasons for it. The first of which is that LTSpice is using a logarithmic scale, so I need to force that to happen. So I can, if I click on my x-axis, which is what I'm trying to do here. So if I click on my x-axis and I hit logarithmic scaling, it scales only the x-axis. And I'm going to need to make sure that everything is on the same scale. So I think I went from 10 millihertz, so that would be 0.01, that'll be okay. And I think I've made this go to 100. Things are looking a little better there. I'm gonna try to make all these numbers look how I want them to, so let's see. I don't know whether or not that particularly helped, but oh well. Another thing that I need to do to make sure that it's matching my LTSpice plot, LTSpice is giving me again a Bode plot where I have a logarithmic scale, where it's taking the logarithm of H of omega. Oh, dang it. All right, I'm just going to retype everything. That'll be easier. And now it should look pretty much exactly like it did. I'm going to change this scale a little bit. I'm going to start it at 0 and end it at, let's say, -60. Why is it being a jerk? Had too many minus signs. There we go. Alrighty, and now this graph looks exactly the same as what I got on LTSpice. I could, if I were so inclined, I think mess around with the minor units on this scale and put it in, instead of having it drop by 6 each time, have it drop by -3 so that I can see where the 3 dB cutoff frequency and all that kind of stuff is happening. But everything is pretty legit. So the reason why I'm mentioning all of this is because you can plot both the magnitude here, and let's go ahead and come down some. Put another plot in. And to plot the angle, I tell it I want the argument of h of omega as a function of omega. And it's going to give me this. But notice the y-axis here is in radians. So let me see if I just type in DEG here. No, so it's not doing the change that I was hoping it would do. So 1.57 blah, blah, blah is pi over 2, which is positive 90, and negative 1.5 blah, blah, blah is negative 90 degrees. Now we saw when we looked at LTSpice, that our phase angle, and we can't look at exactly 0 hertz on this logarithmic x scale, but we saw that it started at somewhere close to 0 degrees, and then if I move this, it's decaying down to negative 90 degrees. So we're getting effectively the same response there. So we can play around with the x-axis here. Let's throw this in a logarithmic thing. And we see that it's looking very, very similar now. So starting close to 0, and then whenever Mathcad starts actually picking it up and doing the calculations, it's going to decay down, and then it settles to approximately negative pi over 2, which is negative 90 degrees. So all of that to say, you can use Mathcad to check your work, because I could write h mag of omega is equal to 1 divided by square root of 1 plus omega times r times c quantity squared. This is what our mathematical expression that when we did the math to figure out what the magnitude was, this is what we got. If we put that here, notice that our graph didn't change at all. So that means our mathematical manipulation of the original transfer function to get the magnitude was correct. We can also, let's sneak it in right here. Let's see. I don't remember what the shortcut is for theta. We could drop that guy in right here. and we can see that our graph doesn't change. So we can check our work using both LTSpice and Mathcad for all of these frequency problems. So I just wanted to make you guys aware of that, because some of the stuff that we're going to do, say next class period, where we're dealing with second order circuits, things aren't going to look nearly as pretty. And so having a way to validate that we didn't make any mistakes manipulating our complex numbers is extraordinarily handy. All right, that's really all I've got to talk about today. I'm going to leave it up to you guys. I'm going to give you a homework assignment that's going to ask you to do this, but to play around with an RL circuit and figure out, you know, how, what kind of filter that's going to give us. All right, any questions on this practical filter that we've dealt with today? All right, nobody's saying much of anything. So I will get this this Zoom video or whatever uploaded ASAP, since I wasn't able to generate any other content to have you guys review, so that the people that missed it can have it and all that kind of stuff. And then I'll get your homework assignment up as soon as possible as well, so that you can start working on it. All righty, have a good rest of your Tuesday, and I will see you guys on Thursday morning.